All right, one more problem for activation energy. This is slightly different than what we did before, a little bit more involved, okay, for this one. So the question then is, a reaction has a first order rate constant of 4.82 times 10 to the negative 5 per second at 25 degrees Celsius and 1.41 times 10 to the negative 2 per second at 70 degrees Celsius. So calculate the rate constant at 90 degrees Celsius. So we're given at 25, 70, and we're asked to calculate at 90 degrees Celsius. So since we are looking at rate constants at different temperature, the only equation that we have to work with is this one, okay, which was what we just used in the other activation energy problem, which is K2 over K1 is equal to activation energy over the gas constant and 1 over temperature minus 1 over temperature 2. Okay, so if you look at all of this, then we are given the K2, K1, no problem, which is for the information that is given to us in our problem, but we are not given the activation energy. Okay, that is what's missing. So this is a two-part problem. In this one, we will first need to calculate the activation energy using whatever data is given to us, and then we will calculate the rate constant at 90 degrees Celsius. Okay, so it's just a little bit different involved problem over here. So let's do one little calculation here quickly. For temperature, convert Celsius to Kelvin. So 25 plus 273 is 298 Kelvin, and then 70 plus 273 is 343 Kelvin. All right, and so the first part of the problem is to calculate the activation energy. All right, and so 1.41 times 10 to the negative 2 divided by 4.82 times 10 to the negative 5, and this is all per second, but it doesn't matter because we're going to cross that out anyway, is equal to EA, that's what we are calculating, and then 8.3145 joules per mole Kelvin, and temperature is 298 minus 1 over 343. Okay, 1 over 298 minus 1 over 343, and this is Kelvin. So yeah, per Kelvin. Then you do the natural log of K values, and you should get 5.68 for this, and this is equal to EA. I'm going to leave the R value as it is. I'm not going to change that to kilojoules. I will leave that as joules. Okay, we can see that later on if we want to change it, but we can leave it like that also. So times 5.295 times 10 to the negative 10 to the power of 5. Sorry, not negative 5 moles per joules, and so then EA is 5.68 divided by 5.295, 10 to the power of 5 moles per joule, and this is equal to 1.07 times 10 to the power of 5 joules per mole. I think I have something wrong here. I think this should be minus 5 there. It should be minus 5, otherwise this can't be 5. All right, so which means that is our activation energy, okay, because activation energy can't be that small, okay, logical, which means this one should be negative. All right, anyhow, you get my gist. So now what we're going to do is, now that we've calculated activation energy, we are now going to calculate the K3, okay, because we're supposed to calculate the rate constant at 90 degrees Celsius. So 90 plus 273 is 363 Kelvin. All right, so then ln and K3 we don't know. We can pick K1 or K2, it does not matter. So let's pick 4.82 times 10 to the negative 5 is equal to, and now we know our activation energy is 1.07 times 10 to the power of 5 joules per mole. And now you can see why I left it at joules, because I still have to use my gas constant, 3145 joules per mole Kelvin, because otherwise I have to convert it again over here. So 1 over 298 minus 1 over 363, and that is over Kelvin. Kelvin goes away. And so then ln K3 over 4.82 times 10 to the negative 5, and after you do this whole beautiful calculation here, you should get 7.73, okay, as your answer. And now for natural log and inverse ln, okay, natural log. And so you should have K3 over 4.82 times 10 to the negative 5 is equal to 2.28 times 10 to the power of 3. And so then K3 is equal to 2.28 times 10 to the power of 3 times 4.82 10 to the power of negative 5. And so K3 is 0.110. And this should be per second, okay, because it's still a first order reaction, and I did not write my units here, but they're over here, okay, so this is per second. But anyhow, that's how you would do this calculation. So it's a two-part problem, not just a one part. One part is to calculate the activation energy with the given values, and then the second part is to calculate the third K value at a different temperature, okay.